So before getting back into strings, I'm just going to talk about another data structure first, and then we're going to use it in the main data structure of today. So the data structure I want to talk about first is a sparse table. Here's the problem I want you to consider, and it's a problem that we have seen many times before. So in the input, I'm just going to give you an array, let's call it A, of n integers. Okay, and this array is not going to change. And I'm then going to ask you to answer a bunch of queries. And every query is basically giving you two indices, I and j, and asking for the minimum element between index I and j. Okay, so I have to return the minimum of k from I to j of ak. Now, of course, we know how to do this with a segment tree. And we also know how to do it with breaking down the array A into chunks of size square root n and so on. But the segment tree approach is better. And if I have a segment tree here, I create a segment tree, the pre-processing time is O(n), and then I can answer each query in O log n, right? So if I have n queries, my total runtime would be O(n) log n. But now imagine that I want to answer the queries even faster. So for some reason, even log n is too much for a query. So let's say I want to answer my queries in. Okay. Now, of course, I can just pre-compute everything. So for every I and j, I can pre-compute the answer to this query. And then whenever the query comes in, I just look in a table and I return the answer. So this would answer every query in O(1), but then my pre-processing time would be O(n) squared, which is not good. So now I'm going to show you how to do the pre-processing in O(n) log n, which is a little bit worse than just creating a segment tree. It's worse by a factor of log. But then you will be able to answer the queries in constant time in O(1). Okay. Now, the idea here is very similar to the ideas we've seen in Fenwick, but it also uses one of the properties of the min operator, which doesn't really exist in addition and multiplication and the other operations we had. So you cannot really use sparse tables for addition. The idea is this. Suppose that I want to query a particular segment here. So I want the minimum of this red segment. Now, when I wanted to do this for addition, if I wanted to find the sum of all the numbers here, I had to have pre-computed results for some segments, and then I had to be able to stitch them together to get exactly the red segments, right? And additionally, these smaller segments that I had could not intersect. But when I'm doing minimum queries, as long as I cover everything in the red area here, it doesn't matter if my segments intersect, right? So I can, for example, let's say if I have pre-computed this segment, the minimum in this segment, and I have also pre-computed the minimum in this segment, I can just take the minimum of these two. It doesn't matter that some numbers are calculated in both because I'm just taking the minimum, right? So if I repeat some numbers, nothing changes to the minimum. Okay, so this is the idea that we're going to use, and we're also going to use some ideas that are kind of similar to Fenwick. So the idea in Fenwick was that I'm going to save or pre-compute the results for segments whose length is a power of 2. But then Fenwick had this cleverer thing of saying at every point which power of 2 I want to consider. Now we're going to be less clever than Fenwick, and we're going to say at every point, I'm going to pre-compute all powers of 2. So what do I mean? I mean that I'm going to have, let's call it, again, an array Q. So this is the answer to query. And basically Q of I, K is going to be the minimum element in the segment starting at index I. So starting at index I, that has a length of 2 to the power of k. So I just look at the segment from I to I plus 2 to the power of k minus 1. And I say, what is the minimum element in this segment? And I call that QIK. Okay. Now, first of all, I want to find all these QIKs in my pre-processing. How many different values of QIK do I have? It's n log n, right? Because I can take n different values and k can take log n different values. But how do I actually calculate these values? Well, it's pretty similar to our calculation for lowest common ancestor, right? So here's the thing. What is QI0? So if I have a segment that starts at index I and has a length of 2 to the power of 0, has a length of 1. It also ends at index I. So what is the minimum element from index I to index I? It's just the element at index I, right? So it's just AI. Okay. Now suppose that I want Q of IK. So this is saying that I'm starting at some index. I'm starting at some index I, and I'm going forward by 2 to the power of k steps. And I want to find the minimum in all of this. Well, in order to go forward by 2 to the power of k steps, I can first go forward by 2 to the power of k minus 1 steps, and then again go forward by 2 to the power of k minus 1 steps, right? So I can basically break this down into 2 arrays, half the size of the original segment. And so what is the minimum in the left side? What is the minimum element here? It's just Q of I and k minus 1, right? Now, what is the minimum element here? So the starting point is I plus 2 to the power of k minus 1. And the length is still 2 to the power of k minus 1. So this would just be Q of I plus 2 to the power of k minus 1, k minus 1. And of course, I want the minimum in the whole segment. So I want the minimum of these two things. So I'll just take the minimum of this, and that's QIK. So remember, I have n log n dynamic programming variables. And this formula shows that I can compute each one of them in constant time. So my pre-processing is just going to take O n log n time. Okay. So pre-processing is in O n log n, which is, again, a little bit like a factor of log n worse than having a segment tree. But it's worth it because I'm going to have better queries now. So let's say that now I want to answer query ij. So the question is, what is the minimum element in the segment that starts from index I and goes all the way to index j? So again, consider my whole array. This is my whole array. And I have index I here, and I have index j here. Okay. I have to cover the whole segment from index I to index j. But it's fine if I cover some element more than once. Okay. So here's the thing. At index I have a bunch of things pre-computed, right? So I have a segment of length 1, a segment of length 2, length 4, so on, all the powers of 2. So let's just take the longest power of 2 that does not reach j, or just reaches j but doesn't go past j. Okay. So take the longest pre-computed array here. And let's say that this one had a length of 2 to the power of k. Okay. How can I find this? Well, I can just look at j minus I and ask what is the smallest power of, what is the largest power of 2 that is smaller than j minus I, right? So that's 2 to the power of k. So I can actually find k in constant time. Now, here's the thing. The length between I and j was greater than or equal to 2 to the power of k, right? But it was less than 2 to the power of k plus 1, because otherwise I would take a longer pre-computed segment starting at I. So if I take a segment of the exact same length that ends at j, if I take a segment of length exactly this much, 2 to the power of k, that ends at j, these two segments are going to cover everything from index I to index j, right? Again, some elements are covered more than once here. I don't care. I'm taking minimum. So I can just look at these two. And again, so this one is basically QIK, the minimum in this segment. But here I have to be a little bit careful. It's like QJ minus 2 to the power of k plus 1 and k, right? So I have to find the starting point. But again, I just start at j, go back by 2 to the power of k steps. So I have to take these two things. And of course, I have to take their minimum and return their minimum. But I'm returning the minimum of only 2 of the pre-computed elements. So I'm answering my queries in constant time. This is O1. Okay. Yeah, this is amazing, of course. And again, when you implement this, of course, it also depends on the fact that I'm assuming a word machine. So I'm assuming that every index actually fits in one of your integers. So you cannot have like more than 2 to the power of 64 elements in your array, right? If I want to do like this bit operations here, finding k in O1, I'm assuming that k fits into your word representation. So anyway, assuming all of those things, assuming the word RAM model of computation, this is doing n log n pre-computation and then answering every query in O1. And I have to say again that this works for min. It of course works for max as well. It doesn't work for operations where you don't have, I guess it's called idempotence. So if you add some elements more than once, your result changes. You cannot then use this. Okay, great. Let's go back to our problems over strings. Now, the problem that we've seen over and over again is that I have two strings. I have a main string and I have a pattern. And the question is this pattern a substring of my main longer string? Okay. We've seen many different ways of answering this. We've seen the KMP algorithm. We've seen tries. We've seen suffix trees. Some of them were actually optimal. We're going to see even more ways of answering this. Now, why am I doing this? Because I really like these data structures. So even if it doesn't give you any new algorithms, I want to teach them anyway. Okay. But it does actually help you solve some new problems. Okay. So here's the thing. Remember that we had tries, and then we talked about compressed tries, and then we talked about suffix tries, and then we talked about compressed suffix tries. This is like a compressed suffix try for this particular string, bananas now. And then we talked about suffix trees, which were basically compressed suffix tries, except that I didn't save the labels. Instead, I just saved their indices in the original string. And we saw that we can do all sorts of really cool things with this. But, and we also saw that we can create these suffix trees in O(n) time. That was O'Connell's algorithm. But it was very complicated. So I want to give you another data structure which is kind of easier to work with, but gives almost the same results. And this is what I call a suffix array. Well, everyone calls it a suffix array. Okay, so what is a suffix array? Let's say that I have a string, again, just like before, I have a string S, let's say banana, And as usual, I add some character to the end of it to show that this is the end of the string. So I have this end of string character. And as usual, my end of string character is smaller than all the other characters I have. Let me write the indices here. So 0, 1, 2, 3, 4, 5, 6. Now, what happens if I look at all the suffixes of this string and I sort them in alphabetical order? Okay, so what are the suffixes of this string? One suffix is just sharp, and actually that's the first suffix in alphabetical order. What is the next suffix in alphabetical order? It should start with A, right? So A sharp is the next one actually in alphabetical order. And then the next one is ANA sharp. The next one in alphabetical order is ANA sharp. Okay, so these were the suffixes that started with an A. Now I have a suffix that starts with B, so in alphabetical order, I will have that one. I will have banana sharp. And then I have the suffixes that start with N. So I have NA sharp, and I have NA sharp. Okay, so 1, 2, 3, 4, 5, 6, 7. Yes, I wrote all of the 7 suffixes, and hopefully I wrote them in alphabetical order. Now, here's the thing. I can also write the indices that were the starting point of each one of these suffixes, right? So this one was the suffix that started at index 6. This one was the suffix that started at index 5. And this one started at index 3. And this one started at index 1. This one started at index 0. This is starting at index 4. And this one is starting at index 2. Okay. This array, this red array that I have on the left is called a suffix array. Okay. This is my suffix array. Basically, it's an array that says if I sort all of my suffixes in alphabetical order, what is their ordering going to be? I'm not going to save the suffixes themselves because this would take n squared memory. I just want to save the ordering. I just want to save this array, which takes only O(n) memory. Okay. Now, as usual, several questions. Why is this useful? How do I even calculate it? Why should I care? Things like this. Okay. So first of all, suppose that I just give you the suffix array. So magically you have the suffix array. Okay, and don't worry how much time has been spent to find it. And let's say that now I give you a pattern. I give you another string. For example, I give you this. And I ask you, does this string exist in the original string S? Is it a substring? How can you answer this? Well, remember that a substring is just the prefix of a suffix. We constantly think about substrings like this. This is the common intuition in all of our algorithms. Every substring is a prefix of a suffix. So when I'm getting something like this, or actually too much, let's just do ANA. So when I'm getting ANA, the question is this a prefix of a suffix of S? But I have all the suffixes of S here. I mean, I'm not saving them. I'm saving them implicitly. I'm only saving the suffix array. But I have them in alphabetical order. So if I want to find ANA, I can just do binary search, right? So just go over this. I mean, these are, again, saved implicitly. But just try to find the ANA by a binary search. So I have 1, 2, 3, 4, 5, 6, 7. I can take the middle one. I can take this one. This is the middle element. And I can say I want to compare P with this middle element. Okay. Now, again, the thing that my algorithm has actually saved is just the index 1. So I know that I want to compare P with the suffix that starts at index 1. And I start comparing. And actually, in this case, I immediately see that it matches. So in this case, my binary search just ends in my very first step, right? I find it. But let's say I had something else. Let's say I had BAN. So if my pattern was BAN, I know that I have to first compare it with the suffix that starts at index 1. And I compare it, I see that the suffix starting at index 1 is starting with A, but the pattern is starting with B. So the pattern is bigger than this suffix. So now in my binary search, I know that I have to search for the pattern here. Now I continue my binary search. The next place to look is here. I know that this is the suffix starting at index 4. So again, these are not saved. Only the index is saved. And the way I access these is by going to the original string. So I compare the N with the B. And in this case, I see that B is smaller. So I know that in my binary search, I have to go up here. So I go up, I get to index 0. I compare, and I see that I find BAN at the beginning there. So I just return that, yes, BAN is a substring, and it's actually a substring starting at index 0. Okay. So the great point here is that I can do the binary search. And of course, it's a binary search. So I have n elements in this array. So my binary search is going to take log n steps, right? So my runtime for pattern matching is going to be O log n. But in every step, I have to compare my pattern P with a prefix of the current suffix, right? So the number of steps that I take can be the length of my pattern. So actually, my total runtime is m log n, where m is the length of the pattern and n is the length of the main string. Now, not optimal, of course, because we know that we could just use a suffix tree and just get OM instead of OM log n. I have a log n factor here. But 2 points. First, it's hard to create suffix trees. I think you would really not like to code that. Secondly, we're going to improve this. We're going to get a better runtime. Okay. But at least I hope that at this point you're convinced that this is a useful thing to have. This suffix array is a useful thing to have because it allows me to do binary search. And this is, of course, much better than just naive searching, which would give me a runtime of OMN. So the n is replaced by a log n. Now, the next question is, how do I actually create this suffix array? Now, again, I'm going to show you an optimal way, but the optimal way is hard. So then I'm going to show you an easier algorithm that is like a factor log n worse. Okay. What is the optimal way? Well, what is my suffix array supposed to be? It's just supposed to be all of my suffixes in sorted order, in alphabetical order. But I can get that from my suffix tree, no? So I have a suffix tree. And remember that in a suffix tree, every one of the leaves corresponds to exactly one suffix, right? And so I can just traverse my suffix tree in alphabetical order. So I'll first get A here, for example, then I will get ananas, na, X, and so on. If I just do an in-order traversal here, I will get my suffix array. And we've seen before that I can get the suffix tree in ON time. So this means that I can create the suffix tree and then just do an in-order traversal on the suffix tree, get the suffix array also in ON time. But the whole point was that I didn't want to code Ukonen's algorithm and create a suffix tree, right? So even though this is, of course, the optimal algorithm because it gives you the suffix array in ON, we're going to find another algorithm that is not quite as optimal, but it's easier. Okay. So let me just copy this and let's talk about how to create our suffix array. Creating the suffix array. Here's the thing. I don't like it that my suffixes have different lengths. I would have preferred it if I was just comparing strings of the same length. Okay, so I'm going to imagine that my string is actually circular. So I'm going to put it around the circle, something like this. Can I draw a circle? Okay, so I have banana and then sharp. So I'm going to just put it like this. Okay. If I look at my string as a circle like this, then I can extend all of these suffixes to have the same length. So the longest one is this one, which has length 1, 2, 3, 4, 5, 6, 7. Let's say I want everything to have length 7. How do I do this? I'll just go around this circle. So this one is starting with sharp, and I just go around the circle after sharp. I get B, A, N, A, N, A. This is again A sharp, so I will just add B, A, N, A, N. And so on. B, oh. Yeah, A, B. Okay, so I filled up this whole thing, and it doesn't really affect the order of my strings, because remember, my end of string character was supposed to be smaller than all the other characters. And I'm just adding this extra information after the end of string character. So it's not going to affect the ordering of my strings. My strings are still in the exact same order, and they're sorted alphabetically. Okay. Now, the next thing is that I look at my strings, in this case, 1, 2, 3, 4, 5, 6, 7. I see that their length is not a power of 2, and I don't like that. I like powers of 2. Okay, so I'm going to extend these strings even more so that their lengths become a power of 2. In this case, I have length 7. I would like to have length 8. So I just continue around this circle, and I add more. So here, this was ending here. So the next character is a sharp. Actually, let me move this a little bit to the right so that we have more space. Okay, so here I'm going to have a sharp, and this one is going to get A, and then this is going to get a B. Okay. So again, I'm not really changing anything. Basically, all I'm saying is that this one starts at index 6, and now my index 6 is here, right? So if I look at my indices around this circle, it's like this: 0, 1, 2, 3, 4, 5, 6. So previously, I started at index 6 and ended at that index. But now I'm just going to continue going around the circle until I have 8 characters. Okay, and I'm doing the same thing here, except that it's starting at index 5 and then going around the circle for 8 characters. Again, this is not going to change the ordering of anything. And in practice, I'm honestly going to ignore anything that comes after sharp, right? Because I really cared about the suffixes, and the suffix is only the part that comes before the sharp. So all the part that is coming after the sharp is just noise, but I want to have that noise because it gives me a nicer table. It gives me a table where all of the strings have the same length, and their length is a power of 2. Okay. And now, basically, I want to sort these strings. But again, as usual, these strings are implicit. I'm not going to actually save them anywhere because just saving them would take n squared time and space. So all I have are these indices, the starting indices. And I also know the length of every string, which is basically the smallest power of 2 that is longer than the length of s. Okay, so I want to sort these. Let me give these strings some names. So these strings, because they have a lot of noise, let's call them n. So I'm going to call this one, for example, n6. This one is n5, n3, and so on. So I want to sort these noisy strings. So this is my goal. Sort n0, n1 to n minus 1. And of course, I don't want to save them. I just want to know what is their sorted order, that I need to know the indices. And that's basically, these indices here are going to give me my suffix array. Okay, nice. So why did I want the length of my string to be a power of 2? Because of course I want to do divide and conquer. So the algorithm is going to be really simple. I'm going to say first, I want to only consider the first one character of all these strings. And I want to sort them based on that. Then I want to consider the first 2 characters of all these strings. Then the first 4 characters, so on. So in k steps, I will consider all of them, assuming that's like the length is 2 to the power of k. Okay. So this is my base case. So basically, I can say this is the property that I want. My property is that after k steps, or let me call them iterations, after k iterations of the algorithm, I want to say that the strings are sorted based on their first 2 to the power of k, 2 to the power of k characters. Okay. Now, again, very importantly, I'm not going to really save all of these characters and so on. So what I'm actually going to save are just these indices and the lengths, like what is k. And I'm also going to save their order, right? So let's do this. Let's do step 0, which means that I want to sort all of my strings based on only their first character. So I'm ignoring everything after the first character. I'm just sorting them based on the first character. So I will first have the string that has a first character sharp. So that's string number 6, right? Then I'm going to have the ones that have an A. So let's say 1, 3, and 5. So 6, 1, 3, 5. Then I'm going to have the ones whose first character is B, which is just 0. And then I'm going to have 2 and 4. So this is the result after step 0. After step 0, I know that if I just sort everything based on the first character, what would their orders be? But additionally, I want to keep track of ties as well. Okay. So what's happening here? If I look at string number 6, it starts with a sharp. If I look at string number 1, it starts with an A. So the first character of string number 6 is strictly smaller than the first character of string number 1. But this is not the case, for example, between 1 and 3. 1 and 3, I've put them in this order, but this order is arbitrary, right? It's just that I was looking at the first characters, they had the first character, so I kept the same order as before. I just put 1 before 3, right? So I want to also make sure that I remember which ones are equal and which ones are not equal. So other than this sorted list, so let's say this is my sorted list, I'm going to also save a rank list, which basically says like, what is the rank of this element? So here 6 is going to be, let's say, at rank 0. You can start counting from 0 or 1 or whatever. Close the door, please. And then 1, 3, and 5 are going to have the exact same rank, right? So all of them are going to have a rank of 1. Just think about university rankings. When two people have the same GPA, they all get the same rank, right? Now, what is the rank of 0? Well, 0 has a bigger starting character than all of the previous ones. So suddenly its rank should be bigger. Now here I can put a 4 or I can put a 2. It's up to you. I don't really care. As long as you give the same rank to the ones that are equal and you give a different rank to the ones that are not equal. And then I have 4 and 2 that start with an N. So I'm going to give both of them rank 3. Okay. So at every step, I'm going to have these two things. I'm going to have my sorted list and I'm going to have my rank list. I need my rank list because when two elements are at different positions in the sorted list, I don't know if they're actually equal or not. Okay, so it's just sorting with some extra information on equality. And it's not going to take more time than sorting. Okay, so this is my step 0. And in my step 0, which is basically like the base case of my inductive algorithm, I'm just looking at the first characters of all of these strings, and I'm sorting them, and I'm getting these things. So sort is easy. It takes O n log n. So I spent n log n time just to do step 0. Now let's talk about step k when k is greater than 0. So imagine that everything is already sorted based on the first 2 to the power of k characters. And now I want to sort them based on, they're already sorted based on 2 to the power of k minus 1 first characters. And now I want to sort them based on the first 2 to the power of k characters. Okay, so take 2 of these take 2 of these suffixes. For example, I don't know, 5 and 4. Okay, so I have the suffix starting at 5, let's say, and going forward for 2 to the power of k steps. And this is the suffix that I want to compare with the suffix, for example, starting at 4 and going forward 2 to the power of k steps. Instead of 5 and 4, I can just say I and j. Okay. So let's say I want to look at the suffix that starts at index I and goes forward by 2 to the power of k steps, and the suffix that starts at index j and goes forward by 2 to the power of k steps. I want to just compare these two and see which one is smaller alphabetically. Now, if I'm naive, I can just compare them character by character. But that would take 2 to the power of k comparisons, right? And I want to do a sort, and I know that if I do a comparison-based sort, my sort is going to do n log n comparisons. So my total runtime would become n times log n times 2 to the power of k, which is bad because in my last step, k 2 to the power of k is going to be bigger than n, right? So the trivial thing is how to get n squared log n. Actually, if you just sort all the strings, you also get n squared log n. We want to do better than this. Now, how can I do better than this? I can basically use the ideas that I had in the previous iteration. I know that in the previous iteration, I had a sorted list where I had basically sorted all the suffixes, all the strings. I shouldn't really call them suffixes. All the strings of length 2 to the power of k minus 1. Okay, so I have these strings of length 2 to the power of k. I can break each one of them into 2 parts: a left part, which has length 2 to the power of k minus 1, and a right part, which also has length 2 to the power of k minus 1. Okay. Now, here's the thing. The question is, compare this whole string with this whole string. Let's first compare their left part. If the left parts are not equal, then the one that has a smaller left part is smaller overall, right? If the left parts are equal, then the one that has the smaller right part is going to be smaller. If both the left parts and the right parts are equal, then they're just equal. They're two equal strings. Okay. So now, in order to compare my strings, I don't have to actually go over my strings. I can just do a constant amount of work for each comparison. And the constant amount of work is that I just ask, is the left part of one of them smaller? If so, that one's the smaller one overall. If the left parts are equal, which one has the smaller right part? And I already have this information because from the previous step, I had the sorted list and I also had the ranked list. So now I can again just use a normal sorting algorithm. It's just that my comparison operator is different. My comparison operator looks at the left side and the right side and so on. But every comparison is done in constant time. So the sort overall is going to be done in O n log n. Okay. And finally, after all of this is done, so I do it for every value of k until 2 to the power of k becomes greater than or equal to n. So until 2 to the power of k becomes the whole string, I will get a sorted list that is exactly my suffix array. Right? So this is how I can compute a suffix array. What is my runtime? So how many different values of k do I have to check? Well, I have to check log n different values of k. And for every value of k, in every iteration, I'm doing one sort. But a sort takes n log n time. And we saw that every comparison is done in constant time as well. So I don't have any other overhead. So my total runtime is n times log squared n. Okay. Now, not as good as the runtime of creating a suffix tree and then using that to get your suffix array, but almost good enough, right? It's kind of, you have a factor of log squared. Okay. Can we do better than this? Well, of course, I know that, again, I can create my suffix tree, but just in this algorithm, can we do better than this? And the answer is yes, because I don't need to use a comparison-based sort. If I use a comparison-based sort, like heap sort and so on, yes, at every iteration, at every step for every value of k, I have to spend n log n time. But remember, I also have these rank lists, right? So the numbers that I'm actually sorting are numbers between 0 to n, if you look at just the ranks. So I can just do something like radix sort, right? And then the sort that I'm doing at every step is going to take only O n time because I know all my values are between 0 and n. Yeah, and since that takes O n time, then my total runtime would just be O n log n. So the log n is because I have log n iterations for every value of k, I have to do one iteration, but at every iteration in this n, I'm just doing a radix sort. So what I'm saying is that I can just look at each string of length 2 to the power of k as a number with 2 digits. The first digit is the rank of the left half, and the second digit is the rank of the right half. And then I can just use radix sort. Okay, so now we have our suffix array in O n log n time for pre-processing. And now we can also answer the problem of pattern matching in O m log n. So it seems we're just off by a factor of log n for everything. So we know that the optimal is O m here and O n in creating the data structure and pre-processing. But now we're just off by a factor of log n, which depending on your use case might not be too bad. Okay. Now, I want to consider some slightly different problems before I tell you how I can actually improve the pattern matching. So suppose that I give you a string. So this is our next problem. In the input, I'm just going to give you a string s. And in the output, you have to tell me how many different substrings does s have. So what is the number of distinct substrings of S. So you can solve this with a suffix tree as well. Basically, whatever I'm doing with the suffix array, you can do with the suffix tree too, right? But I'm going to solve this using a suffix array. So the idea here is that, for example, if S is something like this, A, then its substrings are just the empty string, A, and S itself. So it has only 4 substrings. But if I have something like ABC, then it has many more substrings, right? So it has, for example, AB and BC, which are different, whereas here you just had AA, and this was again AA, so you wouldn't count it twice. Okay. So I've given you a string. I'm asking for the number of distinct substrings of S. Now I'm going to do something really complicated here. And you might think that it's completely useless, but then at the end, we will come back and it suddenly solves this. Okay. So here's the thing. I'm going to take my suffix array. So again, I'm just going to use banana as my example. So this is banana and my suffix array. So let's say that I just want to know how many different substrings that does the string banana have. Okay. Here's what I'm going to do. I'm going to say, what should I call it? I can call it longest common prefix. I'm going to define this thing. I'm going to say LCP, and this stands for longest prefix of IJ, is going to be the longest common prefix of the suffix starting at index I, so of S from index I to the end, and the suffix starting at index J. Okay. And of course, this is the length of the longest common prefix. I'm not going to save the actual string again because it takes a lot of time and a lot of space. So for example, if I want to do LCP of 3 and 1, I'm basically saying, look at the suffix that starts at index 3, look at the suffix that starts at index 1, how many of their first characters match? And in this case, 3 of them match. So LCP of 3, 1 is 3 here. So again, I'm looking at common prefixes of suffixes. Okay. So I want to calculate these LCP values. Okay. More specifically, suppose that I have given you a string S, and suppose that you have already created a suffix array. So you have these red numbers here. And now I'm just asking you a bunch of queries. And every query is that I give you I and J, and you have to give me the longest common prefix of the suffix starting at index I and the suffix starting at index J. Okay. So again, of course, we have to pre-compute some things, and then we have to combine them to answer our queries. So let's talk about the pre-computation that I want to do. I want to say that I look at all these suffixes in the order that they appear in the suffix array. And I'm just going to find the LCP, the longest common prefix, for any 2 neighboring suffixes. So I want the LCP of these two, these two, these two, these two, so on. Okay. So for example, what is the LCP of 6 and 5? It's 0. Nothing matches here. Okay. What is the LCP of 5 and 3? It's 1. What is the LCP of 3 and 1? It's A matches, N matches, A matches, it's 3. The LCP of 1 and 0 is actually 0 because even the first character doesn't match. The LCP of 0 and 4 is also 0 because even the first character doesn't match. And the LCP of 4 and 2 is 2 because N and A match. Okay. So again, I'm going to say imagine that magically I have given you the array in orange. I have given you the LCP values for the suffixes that came immediately after each other in your suffix array. Okay. Now you want to answer queries. I give you two indices I and j, and I ask you what is LCP of I and j. How would you answer these queries? So for example, suppose that you have these orange numbers already, and I ask you what is the LCP of 5 and 1. Yes, we just have to take minimum, right? So if I want the LCP of 5 and 1, let's find 5 and 1 in this suffix array. I have 5 here, I have 1 here. But 5 shares 1 character with 3. 3 shares 3 characters with 1. If I take the minimum of those, that's the amount of characters that 5 shares with 1. Okay, it's pretty easy to see this because, of course, all of my suffixes are in alphabetical order. Okay, so if 6 were to share something with 1, it would have to share the same thing with 5 and 3 as well. Or in other words, LCP of 6, 5 is going to be definitely greater than or equal to LCP of 6, 1, and so on. You can see the other side easily as well. So basically, whenever I'm doing LCP, all I have to do is to first find the two indices I and j here in my suffix array, and then I go to this orange array, which were LCPs of consecutive suffixes, and then I just take the minimum over that segment. Which brings us back to where I started this lecture. You use a sparse table for this. Okay. So what I have done is that first, in my pre-calculation, in my pre-computation, I compute this orange array in addition to the suffix array in red, which I already have. I compute the orange array, and then I create a sparse table on top of the orange array. And again, I already spent n log n time to create the red array, the suffix array. So it's fine if I spend n log n time to create this orange array. It's not going to change anything. It's just a constant factor more. And then now, if I want to answer any query, I can answer it in constant time. So we are at a position where after O(n) log n pre-processing, we can find LCP of ij for any I and j in O1. Okay. Great. Why does this help us? I forgot to tell you how to create the orange array. That's also part of the trick. So I told you, imagine that magically you have the orange array. I forgot to come back and open the magic. So how do you find the orange array? So I want the LCP, the longest common prefix, between each two consecutive suffixes in my suffix array. Okay. Here's what I'm going to do. I'm going to start with my longest suffix. And that's, of course, the suffix that starts at the smallest index, which is index 0. Okay, so I'm going to start with this, and I'm going to compare it with the suffix above it in my suffix array. And I'm just going to see how many matches I get. So between 0 and 1, in this case, I have 0 matches. So I just write 0 here in the orange array. Okay. Then I just continue this. I always take the longest remaining suffix and I compare it with the suffix above it. So now I go to 1, I compare it with the suffix at 3. I see that A matches, N matches, A matches, and then here I have a mismatch. So I know that in this position, I have to write 3. I have 3 matches. Okay, so I have 3 matches between the suffix starting at index 1 and the suffix starting at index 3. Now, I go to the next longest suffix, the suffix starting at index 2. Okay. Now, a naive algorithm would just compare the suffix starting at index 2 with the one above it, the suffix starting at index 4. But I'm not going to do that because I've already compared 1 and 3, and I know that they match at 3 positions, right? What happens if I just ignore the first character of these two suffixes? I just get the suffix that starts at index 2 and the suffix that starts at index 4, right? So if the suffixes starting at indices 1 and 3 matched for 3 characters, the suffixes starting at index 2 and 4 are going to match for 2 characters, right? It's just that these are literally the same, except that I don't have the first character here. So I already know that this one matches this one. And of course, here I don't have a match, so this is 2. I don't have to do any rematching of something that has already been matched. Okay. Now I continue. I go to the next longest suffix, that's 3. Okay, so I want to compare 3 and 5. But I know that 2 and 4 matched for 2 characters. So I already know that the first character of 3 and 5 is going to be a match. So I don't check this. I start from the second character and I already see a mismatch there. So this is just going to be length 1. Okay, now I go to 4. I want to compare 4 and 0. Right? Can I use the same idea as before? What can I do here? If I want 4 and 0, was there anything else that I could chop one character from the beginning and I would get 4, 0? Well, if you look at it cyclically, yes. If you consider this array instead of this one, we said, I mean, they have the exact same alphabetical order anyway. So I can always consider this one, right? So if I consider this one, then I want to compare 4 and 0, but I can go one character before. I can compare 3 and -1. But what is -1? -1 is 6, basically. It's cyclical. Okay. So the question is, how much of a match do I have between 3 and 6? But I don't really have anything there. I don't have any information there. So I'll just start matching and I see that they don't match. So because they don't match, this is also 0. Okay. Finally, 5. I take 5 and I want to compare 5 and 6. Okay. In order to compare 5 and 6, I can ask myself, do I know anything about 4 and 5? Do I know anything about 4 and 5? What do I know about 4? I know that 4 is below 5. Right? And I know that the minimum of these things is 0. So it's not really going to help me anyway. So I have to compare these two and they don't match. And this is 0. So this is basically the algorithm. The algorithm is simply just go and try to match. But whenever you already know that some things match, because you know that I-1 and J-1 had a match before. Now, this might not be a direct match. Maybe I-1 was matched with something else and J-1 was somewhere in between. That's also okay. So in cases where you know that there is already a match, you don't do the match again. You just jump over it. Okay. And with this, it's actually quite easy to show that the total runtime becomes ON. And the proof is literally the proof of the KMP algorithm. It's pretty much the same thing. So you can just write this as a pseudocode, and then you can look at the variables. You can argue about when do the variables increase, and you say they cannot decrease more than they increase. Yeah. So finally, we have all of these things in ON log n. And after we have them all in O and log n, I can answer every LCP query in O1. Okay. Now, back to our problem. I have a string S. I want to know how many different substrings does S have. How do you find that? Well, I claim that it's just the sum of the numbers in my orange array. Okay. Why? A substring is a prefix of a suffix. So I can just go over all of my suffixes in alphabetical order, and for every suffix, just count how many new prefixes is this suffix contributing. Okay, so this first suffix, I mean, this is just the end character, so you can count it or not, it's up to you. This second suffix 5, it has a length of 1, so it has one prefix. The question is, was this prefix there before? And the answer is no, because it doesn't share any prefixes with the previous one. So this one is contributing a new prefix. It's contributing one new substring. Now, look at the suffix starting at 3. It has a length of 3. Okay, so it's contributing 3 new substrings, 3 new prefixes, but one of them was already contributed by the previous one, by 5. So it's actually contributing to, oh, okay, sorry, it's not the sum of these numbers. It's the sum of lengths minus these numbers, right? So I can just write down how many new prefixes each one of these are contributing. So 5 contributed 1 new prefix, 3 contributed 2 new prefixes, 1, it has a length of 1, 2, 3, 4, 5. So it could potentially contribute 5 new prefixes, but 3 of them were already contributed by 3. So it's adding only 2 new prefixes, and so on. You can just write these. Okay, let me just do it. So this one is 1, 2, 3, 4, 5, 6 minus 0, so it's contributing 6. This one is 2 minus 0, it's contributing 2. This one is 1, 2, 3, 4 minus 2, it's contributing 2. And then the sum of these numbers is the total number of distinct substrings that I have. Okay, so after all of this, it means that when I give you a string like this, you can answer in O n log n what the total number of distinct substrings is. Okay, but let's look at a different problem that we solved when we were doing dynamic programming. So this is the longest common substring problem. So my input is going to give you 2 strings, S1 and S2. And as the output, you have to tell me what is the longest string that is a substring of both S1 and S2. So what is the longest pattern that appears in both of them? You can ask for the string itself, or you can just ask for its length. It doesn't really matter. Length of the longest common substring of S1 and S2. And let's imagine that S1 has N1 characters and S2 has N2 characters. Now, we've seen with dynamic programming how we can, actually, that was a homework for you. So hopefully you have seen with dynamic programming how you can solve this in ON1 times N2. Okay, or if both of them have lengths n, let's simplify it. Let's say they both have lengths n. You've seen how to solve it in ON squared. We want to solve it faster. We want to solve it in ON log n. How would you solve this faster? So let's call this common substring T. I want to ask what is the longest T that is a substring of both S1 and S2. Now, your first intuition might be, well, we're talking about suffix arrays. So let's create a suffix array of S1 and then let's create a suffix array of S2. But that's actually not a good idea. The better idea is to just glue the two strings together and create a suffix array of the whole thing. So let me do a very short example. Let's say I have ABBA and S2 is BABA. Okay. Oh, this is already too long. Let me do even shorter. I have ABB and BBA. I want to ask, what is the longest common substring? It's BB. Okay. So what I do is that I just put them together. So I create ABB and then end of string character and then BBA. I can have another end of string character at the end. I don't really care at this point. So let's create a suffix array of this string. Okay, so I have to put the suffixes in alphabetical order. And we said that this end character comes before everything. I can have another end character here as well. Technically, you should have two different end characters, I think. No, actually, this works. Yeah, this works. Okay, so I have this one, which is the first suffix in alphabetical order. I have another suffix that starts with the end character, BBA. Now, I have suffixes that start with A. So this would be A end character, and it would be the whole thing. A, B, B end character, B, B, A end character. And then I have the suffixes starting with B. So in alphabetical order, I actually have B end character, B, B, A end character. I have this one. So then I have this one, which is BA end character. Then I have this one, BB end character, BBA end character. This is really hard to do. Okay, 1, 2, 3. I have another one, right? So I have BBA end character as well. These are the suffixes ending with B. Okay, so this is my suffix array. Again, the suffix array is actually the indices, not the suffixes. Okay, but here's the thing. When I have this suffix array, I know which one of these suffixes start in the first string and which one of them start in the second string, right? So my first string is going to have indices 0, 1, and 2. And then there is this 3. And then my second string is going to have indices 4, 5, and 6. And then there is this endpoint, which is at index 7. Okay, so if I look at these suffixes, I know which ones are starting in my first string and which ones are starting in the second string. Now, consider the longest common substring. In this case, the longest common substring is BB. What's going to happen? Well, basically, the string that starts at this first B at 1, the suffix starting at 1, and the suffix starting at 4 are going to be neighbors in my suffix array, right? Because they're starting with the same string. So given that they're neighbors in my suffix array, and I can find them here. So this is BB, it's this one. And then I have this one. And given that I know where they started, I know that they started in different strings, I can know that BB is the longest common substring. So basically all I do is that I create my suffix array. Again, this is my suffix array. This is corresponding to 7. Actually, let me color code it. This is 7. This one is the one starting at 3. This A sharp is the one starting at 6. So this one is in my second one. This B sharp is actually starting in the, oh, let me use different colors. So I use red for the first one. Okay. So I have A, B, B sharp, blah, blah. This is the one starting at index 0. I have B sharp. This is the one starting at index 2. And this one is the one starting at index 5. And this one is the one starting at index 1. This one is the one starting at index 4. So I can just color code it so that I know which ones started in my first string and which ones started in my second string. And now I can just create this orange array, which tells me how long the common prefix is. And basically, I'm looking for the longest common prefix between two suffixes that start in the two different strings. So I'm looking for the longest common prefix between the ones that go from green to red or from red to green. And again, as soon as I have this orange array, I can just go over it once and I can find it. Okay. But now we have 5 minutes. Let's get back to our original problem, the most important problem of this part of the course, which is pattern matching. So again, my problem is that I've given you two strings, a big string and a pattern. The question is the pattern a substring of the big string? Okay, so my input is again two strings, S and T. And the question is T a substring of S? And as usual, I'm assuming that S has n characters and T has m characters. Okay, we've already seen that we can solve this with a binary search, right? And if I do a binary search, we saw that the runtime would be m log n. Okay. The question is, can I do better than a binary search? Or can I do my binary search in a better way? Because actually, I mean, my binary search is giving me the log n here, but the m is coming from naive matching because I was taking my pattern and I was just comparing it to each one of the suffixes naively, right? So can I use some external information, maybe this orange array that I computed here, or maybe this LCPs? I know I can find each one of the LCPs in O1, right? So can I use these LCPs to make my pattern matching faster? Okay. So let's do this. Let's just take the same thing. I have to copy it from here. Okay. So let's say that this is my suffix array. And remember that I have done the pre-processing. I have computed this orange array. And so now if someone asks me what is the longest common prefix of the suffixes starting at index I and index j, I can answer that in constant time. So I'm going to use an algorithm that relies on these longest common prefixes to do pattern matching faster. Okay. Here's the algorithm. I'm going to do binary search. But before doing binary search, let me just show it to you as a tree. So this is my suffix array. So I can write it like this. I have 6, 5, 3, 1, 0, 4, and 2. And okay, so the problem here is that I want my length to be a power of 2. So if my lengths were to be a power of 2, I would have more of this, but that's fine. Look, what do I do when I do a binary search? I first compare with index 1, right? So I can actually create a binary search tree that kind of shows me how my binary search works. The way it works is that I always compare with index 1. And if it's smaller, then I compare with index 5. If it's bigger, then I compare with index 3. If it's smaller, then I compare with index 6. If it's bigger than 1, I'm going to compare with index 4. If it's smaller, I'm going to compare with 0. If it's bigger, I'm going to compare with 2. Okay, so this is a binary search tree of my suffixes in the alphabetical order, basically. And I'm doing these comparisons. Okay. So whenever I'm doing binary search, I can imagine, I mean, again, I'm not saving this in my code. This is just implicit. This is for me to think about the algorithm. When I'm doing the binary search, I can imagine that I'm doing a search in this binary search tree. Okay. So let's say that the pattern I'm searching for, the pattern P, is ANA. Okay. Now, at the top of the tree, I'm going to compare ANA with my suffix 1. So I'm going to compare it with this one, and I see that the first 3 characters match. Okay, but then I see an N here, which is not in my pattern, so my pattern is smaller. So in my binary search tree, I have to go left. But then when I go left, I suddenly forget everything that I knew so far. I forget that I had matched 3 characters with 1, right? And now I start matching with 5, and I see that I can match only 1 character. But I could have done something better, right? So I know that the first 3 characters of my P matches my string 1, my suffix 1. And then I went from 1 to 5. When I go from 1 to 5, I can also ask how many of the first characters of 1 and 5 are the same. What is the longest prefix of 1 and 5? And that's already 1. Right? So I should already know that the first character is going to match. And if the first character is going to match, when I go to index 5, I'm not going to start matching the first character. I'm going to start only matching from the second character. Okay, so here I saw that I have 3 characters in common. I go to index 5. Already I know that the first character is going to match because the longest common prefix of 1 and 3 is 1. And the longest common prefix of my pattern and 1 is 3. So the longest common prefix of my pattern and 5 is going to be at least 1. So I know the first character matches. I'm not going to compare the first character. I compare the second character, and I see that the second character is bigger than 5. Right? So the second character is N here. It's bigger than sharp here. So I know that in my binary search tree, I have to go right. So I know that I have to compare with 3. But when I want to compare with 3, again, what do I know? I know that 3 and 5 already match the first character. And I know that my pattern and 5 already match the first character. So I know that I don't have to compare the first character of 3 with the first character of my pattern. But I know even more than that. I know how many common characters 3 had with 1, right? 3 and 1 actually have 3 common characters. Because again, I can just ask a query. I can ask LCP, and I can ask what is the number of common characters between 3 and 1. And the number of common characters between 3 and 1 is 3. But I also know that the number of common characters between my pattern and 1 is 3. So I know that the first 3 characters are going to be the same in my suffix 3, suffix 1, and my pattern. So I don't need to compare the first 3 characters. I know that they match. And well, good point here. My whole pattern is 3 characters, so I know that everything matches. I don't have to do any comparisons at this point. I already know that they match. So generally speaking, whenever I am at any node of this tree, I have seen all of its ancestors, right? But what are the ancestors that I really care about? I care about the closest ancestor of this node that is to the left of it. So the closest ancestor of 3 that is to the left of it is 5. And I care about the closest ancestor of 3 that is to the right of it, in this case 1. And because I already know how many characters, what length of prefix my pattern shares with any of these ancestors. And I can also ask how many characters are shared between these ancestors and this node that I am at. I can avoid doing a lot of extra matching. Okay, so that's my algorithm. Every time I only match things that I have any doubt about. Otherwise, if I know that something is already matching, I'm not going to match it. Now, I'm going to also give you a video about this, which explains all of the cases in more detail. The casework is really easy, but the idea is the important one. Basically, what happens here is that whenever you have something matched, you will never get it unmatched. So you're starting at the top of this tree, and you're going down the tree, and you're finding more and more matches. Okay. What do I mean by you don't get it unmatched? Like I started with 3 here, and I went down to 1. I mean that when I find a prefix, when I find a common prefix between my pattern and my current string of length 3, I will never have to compare anything about the first 3 characters. Why is that? Because I had a match of length 3 here, and I went here. Now, at this point, I know that this one, 5 and 1, only share 1 character. Additionally, I know that 5 came before 1 in my suffix array. So I don't actually need to compare the second character. I know that my pattern is bigger than 5. Right? Because 5 was smaller than 1, and they shared the first character. So the second character of 5 is already smaller than the second character of 1. But my pattern matched 1 for the first 3 characters. So my pattern is definitely going to be smaller than 5. So when I'm going in this tree and I'm getting to vertex 5, I would never do a comparison of characters. I already know that I have to go right. The only cases where I do comparisons of characters are when my matches are actually increasing. So as I'm going down this tree, I start at the top, keep going down. In every step, I either find more matches of characters, or I go down the tree. I can match at most m characters, and the height of this tree is log n. So my total runtime is actually OM plus log n. Because at every step, either I'm finding a new match, a new character match, or I'm going 1 step down this tree. So that's how I get m plus log n, which is of course better than m log n, but still it's not optimal, because we know that if we just used suffix trees instead of suffix arrays, we could just get OM. But the whole point is we don't want to implement O'Connell's algorithm. Okay, I'll see you next week.